Okay. Let me make sure I can get my thing sharing. Hmm, that's really annoying, actually. Okay, I might need a minute or two. I'm sorry about this. Okay, I think I've got it. Let me just make sure I can share. Awesome. Oh my gosh. Can you guys see my slides?
Yeah, we can see them.
Okay. Can you also hear the cat? I'm gonna remove him. Okay. All right. Okay. Awesome presentation, Val. Um, really good job with that. That was, I think, wonderful for getting people introduced to neuroscience basics, getting into research as an undergraduate. Let me just do one more thing here. Screen. Oh, okay. Okay. All right, it's fine. I won't have presenter view. That'll be all right, I think. Or let me try this. Sorry, my two monitors are just not playing right.
Right now we see the presenter view.
Oh, that's so annoying. Okay. I'll just try to swap it back and it'll be fine. Oh, now do you see the actual normal view?
Yes.
Yay. Okay, wonderful. Okay. So, hi everybody again. I'm Danny. It's so awesome that you're all here, on a Sunday, interested about neuroscience. So, you know, we've got 40 minutes now. I don't need to get through all my slides or I'll bounce around to the important ones, but like, please interrupt me with questions if you don't understand something. If you want to dig into something a little bit more, I'm happy to talk about that. I want you guys to get something out of this. Okay. Yeah, so I'm a third year. I work with Dr. Nigel Peterson, Dr. Christelle Anaclay, and I'll be talking about the relationship between epilepsy and sleep. So, just like personal background really quick, but I grew up around Des Moines, Iowa, actually like a little bit north in a suburb called Ankeny. And then I went to Madison, Wisconsin for undergraduate. Super beautiful campus if you ever get the chance to go. And I actually started in a plant pathology lab and I transitioned over to a neuroscience lab in my junior year. So this was kind of the team, and they were actually one of a very small number of labs that work in sleep and epilepsy. And so what's really cool is that I got to come here to Davis now, and I get to keep working in that same sleep and epilepsy subfield. So this is like the current, or Brandon's actually graduated, but these were some of the grad students in the lab. This is the neuroscience grad group playing cornhole. It's just been a really wonderful community here. I really like Davis. So a quick introduction to graduate school because I was told that might be useful for some of you and you might be unfamiliar with it. So this will be like really um, pretty basic stuff, but I think if you've never thought about graduate school, you might not know some of it, so it might be useful. Master's degrees are the shorter ones. They take a year or two. Usually in STEM, I've seen 2 years, and it wraps up with completing a thesis or a final project. And one thing important to know is that in that process, you are the one paying tuition. I don't think maybe there's some masters in which people are paid to do them, but I'm not super aware of them. Uh, for a PhD, it's a much longer process. It's 4 to 7 years. Neuroscience averages about 5.5. Sometimes people take about 7 because they have a kid during the process. I know some people that did that, and obviously that just takes a while to get through the actual schooling. And something important to note too is that you're only taking classes for a year to 2.5 years, and then you're just a full-time researcher. And even during that time that you're taking class, you're still kind of your main focus is always research. So it's a lot different than undergraduate in that way, in which if you're doing research than undergrad, it's usually coming second. And then it completes in a dissertation. And so this is a novel contribution to advancing the scientific field. And one thing that's not maybe people aren't aware of if they're not super close to someone who's done a PhD, but during that process, you are actually paid. You are not paying tuition out of pocket. So you're paid full time for your work all those years. Your job's very secure, so that's a big plus of it. And then you're paid either through your lab, you earn a grant for yourself and support yourself, or if your lab doesn't have the funds to support you, you haven't earned a grant, then that's and it depends on the program. In neuroscience, we only have to TA a quarter, but in things like mathematics, I know some people that have to TA every quarter. So, yeah, that's kind of a broad overview. Some advantages and disadvantages. I think in a PhD, it's a lot of kind of double-sided stuff, where the good stuff's also the bad stuff. You get to choose your own hours. So I really like this little comic. You can work whenever you want. Every day is a Saturday, and then you work on Saturdays. So I think that one captures it pretty well. But I don't know. A lot of you in undergrad, you're kind of already experiencing that with coursework and homework and all that. You get to develop a variety of skills. I like this comic as well, where you're really excited about trying an experiment for the first time, and then it just becomes, your arch enemy trying to get something really cool to work. But yeah, you get to spend time writing and doing actual research with like cutting edge tools, and then also mentoring. So it's a lot of different skills you get to work on. You have the same boss for many years. That can be great if you love your boss. It can be really hard if you don't. So it's important to find that right mentor fit. And then I think most exciting about a PhD is you get to contribute new knowledge. Kind of the moment for me, we had these neurons growing in a dish. They had tau, which is a protein involved in Alzheimer's disease. And these were the firing rates. These are spikes that a neuron fires, and the firing rate was very impaired. Then we washed on this drug called adipiron, and we saw for the first time that washing on this metabolic drug increased firing rate, tenfold. And then now they've gone and continued this work and done it in animal models and shown that it works there instead of just cells in a plate. So I think it's pretty awesome to be able to contribute to something new in this great big world, and also have that be built even when you've moved on to a different project. Uh, I'd say the hardest thing, honestly, I think the hardest thing about graduate school, or maybe particularly a PhD, was just getting into the program because they're very competitive. Um, but to go along with that, it's it's okay to do gap years. I've met some undergrads at events who were interested in grad school, and they're apprehensive about gap years. Um, I think maybe because the older generation didn't really take them, or maybe the term gap year, they're trying to change it to be more like bridge year, because really you're going to be doing full-time work. You're going to learn that you like research full time. Um, I did one and I really enjoyed it, and it makes you more competitive for this process. So don't be afraid to take time off between the two if you're interested. Okay, I guess with that, now I'm gonna transition over to talking about epilepsy basics. So does anybody have any questions? Feel free to ask them in the chat or unmute just about, I don't know if anyone has any big questions about just what grad school looks like. Okay, I think there actually are messages in the chat. If I can. Okay, okay. No, we're good. All right. Okay. So I will keep on rolling then. So epilepsy. So this is going to be kind of my wordiest slide, but it's important to get these definitions out there. So epilepsy is a neurological disorder characterized by an enduring predisposition to generate epileptic seizures. That part, enduring predisposition, is really important. If you're in a car accident and there's some kind of traumatic brain injury and you have a seizure in response to that, you don't necessarily have epilepsy. A single seizure in response to some kind of injury or event or a fever as a child sometimes cause seizures. That doesn't mean that you necessarily have epilepsy. Epilepsy is that spontaneous, it needs that spontaneity where it can emerge out of nothing that you're having a seizure. And then what's a seizure? Also very important. This is very wordy, but I just wanted to get an official definition. So it's a transient behavioral change that might be objective signs. So objective signs, you think of the, tonic clonic on the floor, uncontrollable movements, or subjective symptoms such as loss of awareness. So there's a whole type of epilepsy called absence epilepsy, which is just absence, but French, because that's how where it was discovered. But absence seizures where people will just almost zone out and then come back and they won't realize any time has passed. So both of those are different types of seizures, and they're caused by abnormal, excessive, or synchronous neuronal activity in the brain, which I'll have an example of shortly. And it's important to recognize it affects a really broad population of people, 70 million worldwide, approximately, roughly 1% of the world's population. So it's a big population of people suffering from this disorder. I'm not going to go through this whole table, but just different risk factors for developing epilepsy. If you just think about what can mess up the ways your neurons are wired in the brain, right? Head trauma makes sense. Stroke, a tumor growing, a family history of seizures, something during development, an infection, really anything that can, cause an abnormal change in the brain can be a risk factor for epilepsy. So now what I'm going to show, and this might be a little intense because it's going to be a mouse having a seizure, but you're all interested in this stuff. But might be a little intense, but I think it's the best example. I'm going to have a video of one of our mice here, and then in real time, it signals. So this is from the head plate that Bao showed you. We put a head plate on the mouse's head with those screws. The EMG, or electromyography, is for movement. And then ECOG, or electrocorticography, is the screws that are going through the skull, resting on the dura, the skin of the brain, and that picks up the neuron's electrical signal. So we're actually getting real-time electrical signals from movement on top and then from the brain itself. And so this is typical activity, and the mouse is moving around. And then here, right, going back to that definition, it's abnormal, it's synchronous. You have these really, really intense, this really intense neuronal pattern of electrical activity in the brain of those neurons firing emerges. And the mouse is having some automatism. So you just kind of do the same repetitive movement. So here it's having its forearms go repeatedly. And then here it's actually going to start jumping around. And this is sort of a tonic-clonic seizure. A person's not as light as a mouse, so they're going to have those spasms on the floor, but a mouse is lighter and can kind of fling itself around. This is also part of a seizure, the post-ictal state, or I guess it's what comes after a seizure, but It's almost like the brain is so worn out from all that crazy activity that there's almost silence in the brain. So yeah, so that's also a part of a seizure. So consciousness hasn't normally returned yet. Okay. So for classifying seizures, there's obviously like unknown, if you can't figure out exactly what's going on, or unclassified if it's not classified yet. But otherwise, the two big groups are focal onset or generalized onset. Focal onset means that we can figure out that the electrical activity is emerging from the same region of the brain repeatedly. There is some local issue there. There's a tumor there that's disrupted the circuit. Now the seizures originating from where that tumor is disrupted, something like that. Generalized onset means that the seizures are happening, they can originate in different places in the brain. It's not a consistent focal region. So maybe, there's these ion channels that allow different ions to flow in, control firing. Maybe they have some kind of mutation, they're letting too many ions in, and these seizures can originate almost anywhere in the brain. So really you define the seizure type, and then you're going to consider these other factors such as structural, right? If you take an MRI and you see a tumor in the brain, that's going to make you think, okay, maybe it's more of a focal epilepsy. Um, and then generalized seizures are usually more genetic, right? Like I said, that channel mutation. So you're going to consider all these factors and what you know about the seizures to give an epilepsy type, which is once again focal, generalized. You can have combined generalized and focal, or you just, I don't really, yeah, I guess unknown is you just can't figure it out with the tools you have. So those are the broad categories of epilepsy. I think it's worth, I like this paper that looked at 1,000 people with epilepsy and just asked them about their perspective. And so one thing I think is important is what induces seizures. Stress is something a lot of people say, missing medications, which is the frontline treatment, which we'll get to. Sleep problems, which is very relevant to my own work, is very high up there. So these different factors can also precipitate seizures. And then they also just ask them, what do you think your epilepsy affects? And here they're agreeing somewhat or completely, and performance in school, ability to remember, ability to concentrate, mental and emotional well-being. It really affects so many things in a patient's life. It's a really uh, debilitating disorder. And then finally, this paper polled over 3,000 people with epilepsy and just found they had higher rates of all these neuropsychiatric disorders. Here, the blue group is epilepsy. You can see they have more anxiety, depression, bipolar. They have more pain disorders as well. So there's tons of what we call comorbidities of epilepsy. It's not just the seizures, it's also what the seizures are causing or what's associated with them. It's also important in epilepsy, perhaps the greatest, or I would say the greatest risk is simply sudden unexpected death in epilepsy, or SUDEP. So it's the most common category of epilepsy-related mortality. Um, of course, since it's sudden, you're not always directly observing the patient or the individual when this happens. But from the ones that have been being recorded in like an epilepsy monitoring unit, this typically always follows a seizure. And if you're just looking at SUDEP in young adults with epilepsy, their risk of sudden death is 27 times higher if they're epileptic than control populations. So that's a frighteningly high number, and it's caused by respiratory dysfunction in many cases. And it also mainly occurs during nighttime sleep. So here's some SUDEP cases, and they have unknown sleep-wake state where they think they were awake, where they think they were asleep. So it seems to happen much more when patients are asleep. And they're also ending up in a prone position on their stomach. So their head is in their pillow, and that's contributing to their inability to breathe. And a couple more graphs here. If you just look at number of deaths for SUDEP, right? So from epilepsy, the number of deaths is really minimal. Only 3,000. I'm not sure if this was on an annual basis or what exactly, but it's very minimal compared to Alzheimer's or stroke. But Alzheimer's and stroke are taking people to very late age in life. If we actually look at this is years of potential life lost. they're losing many years of life. SUDEP's taking a lot younger people than Alzheimer's or stroke typically are. So it's really the second biggest burden of the neurological disorders. So, how do we go about treating epilepsy? The frontline treatment is anti-seizure medications, and over many decades, there's been the development of dozens of anti-seizure medications. They typically modulate the excitatory inhibitory balance in the brain. So they either do that through manipulating voltage-gated ion channels in neurons or enhancing GABA inhibition, which is the main inhibitory neurotransmitter in the brain. However, there's a lot of issues with these medications. 25% of patients quit due to side effects, and 10 to 90% report side effects. It depends on the methodology. If you ask them, do you have any side effects? And then you have them freely report, only about 10 to 40% are actually going to be like, oh, yeah, I have that issue. But if you say, here's a checklist, do you have any of these? People are much more likely to report things. So that's 60 and 90% report that they have side effects. And most of those common side effects are drowsiness, fatigue, dizziness, irritability, and memory problems. So pretty bad side effects. So one other thing to look at is with the development of all these medications, how has treatment improved? Surely, with all these medications, it's improved. I'm not showing the data here. I will show it in a second. I just want to orient you to what it's going to show. We have three different patient populations, all at the same hospital. They either started treatment in the 80s, in the 90s, or in the early 2000s. And they're going to track their probability of 1 year seizure freedom over those patients' treatment duration. And you'd think with better and better drugs, we'd have better and better treatability, but really all three patient groups have trended exactly the same. There remains this quarter of patients that no matter how many different drugs we developed or try or combine, it's not helping them reach seizure freedom. So we need like alternative approaches to reaching that. Some of the alternative approaches is actually removing the epileptogenic zone, right? If you have a focal epilepsy and the seizures are originating from a single place, you can actually just remove that part of the brain, which is a pretty crazy idea if you're not familiar, because it sounds a bit, I don't know, barbaric to just take a chunk out of the brain, but it's still being done. It's done at the UC Davis Health Center here. It's done at a ton of hospitals around the world. And the most common way of figuring out where is that focal region of the brain we're going to cut out is stereoelectroencephalography. It used to be that you'd put a grid of electrodes onto the brain, but now we use these targeted probes to go into the brain. And obviously there's no pain receptors within the brain, so you can, under anesthesia, you put these in, but then the patient can sit with them and wait until they have a seizure that they can record and then figure out where it's originating from. This is kind of gross if blood grosses you out, but here is a piece of brain that's been removed from a patient. And so they took out the region where the seizures were coming from, that dysfunctional circuit. And I'll show you some stats here in a second about how that actually helps a lot of patients. A different method of cutting out that epileptogenic zone or removing it is not cutting out, but using a laser to ablate it. So you actually go in with a laser probe, you target that region, you're using MRI to figure out how hot it's getting, so you don't want the brain to get too hot and get damaged in places you don't want it to get damaged. And you actually use a laser to break up that dysfunctional circuit. So how effective is this surgery? It's actually highly effective. So for 58 to 66% of patients, they've been seizure free for 5 or more years after that treatment, which is a lot of seizure freedom. Typically, seizure freedom is just you define it as 1 year, but this is long term. This is 5 or more years. Over half of patients don't have another seizure. So that's awesome. And then also just building on this in a logical way, if patients have a MRI visible lesion, if you have a tumor or if you have clear damage in a region of the brain, when you go in to cut out that part of the brain, they have much more higher rates of success. If there's that cleared lesion on MRI, 2.5 times more successful than if the patient has no lesion, which makes sense. For the sake of time, I'm gonna go ahead and just breeze through these, but there's also three different ways for stimulating the brain to yeah, for stimulating the brain to reduce seizures. They don't often cure epilepsy, but in about 50% of patients, they reduce seizures by about 50%. So it is helpful for ameliorating that burden, but you do need an implant. Um, and once again, they're only so successful at reducing seizures. So an alternative that we're interested in the Peterson lab and the Fuller lab, is this relationship between sleep and epilepsy. I've already talked about how patients will say if they get worse sleep, they're more likely to have uh, more seizures. And so epilepsy, as I've said, is defined by seizures, these synchronous neural events, and IEDs, which are these interictal epileptiform discharges. Ictal just means seizure. So between seizure, epileptiform discharges, you don't typically see these in a normal brain. And both of those have actually been shown to disrupt sleep-wake by causing sleep fragmentation. And conversely, if you sleep deprive a patient, it actually increases their amount of seizures and IEDs. So there's this reciprocal impairment between the two where you have more seizures, worse sleep, more seizures, worse sleep. Anti-seizure medications are typically effective at reducing seizures, but don't usually affect the amount of IEDs or measures of sleep-wake. What's been shown is that sleep interventions, this is particularly the treatment of epileptic patients that also have obstructive sleep apnea. They gave them one of those CPAP machines to help them breathe better, and they had improved sleep wake. They had reduced sleep fragmentation, reduced sleep deprivation, and simultaneously reduced seizures and IEDs. And this has been shown in 6 studies now. So it's really encouraging that sleep interventions may be another point of treatment for people with epilepsy. I'm going to skip that slide. I will jump to here, actually. So that serves as my primary basis for my thesis work, that the treatment of obstructive sleep apnea in epileptic patients improves sleep quality and seizure control. However, no studies investigated whether directly enhancing sleep improves epileptic outcomes. Those studies that treat obstructive sleep apnea are also improving respiratory rate. They're changing blood oxygen levels, and some groups think that that's leading to differences in inflammation, and that's changing the seizure rates. We think it's the sleep, but that has not been directly shown yet. So we hypothesize that enhancing slow wave sleep in epileptic animals will improve seizure control. And my approach to that is that I will enhance slow wave sleep through activation of the GABAergic neurons in the parafacial zone in mice with temporal lobe epilepsy. So this is that sleep model that Bao talked about, but I'll briefly show it again. So we want to chemogenetically activate the GABAergic parafacial zone. So I will walk you through that. So the parafacial zone is a brain region in the brainstem of the mouse that sends inhibitory GABAergic projections to this red wake promoting circuitry. So when the parafacial zone is active, it inhibits that red wake promoting circuitry and causes slow wave sleep. So we want a way to increase slow wave sleep on command. Our solution to that is chemogenetics. So we inject a virus, which you saw Bao had a nice like real photo of earlier, but we inject an adeno-associated virus into the parafacial zone. And what this does is that virus goes in and it causes the expression of designer receptors. And we can target those designer receptors with a designer drug. So we're giving the mouse a drug that only acts on those receptors we put in, which is going to enhance sleep. So we give the drug, it activates the GABAergic parafacial zone, inhibits the red wake promoting circuitry, and increases slow wave sleep on command. This is the most targeted model currently for enhancing sleep with no side effects. You know, there's different sleep aids on the market for people that we could give to epileptic patients, but then those sleep aids do all kinds of other stuff in the brain. They act very broadly. So we wanted the most targeted way of enhancing slow.
Danny, I don't think I can hear you. I don't know if that's only on my end.
Yeah, sorry, Danny. I think you might be on mute or something on unplugged, maybe.
But hello.
Hello, hello. Could you guys
Oh,
hear me?
I'm back.
Wait.
Hi. Yeah, we can hear you now.
Oh, okay.
Okay. Sorry, guys. I think I was lagging out quite a bit, but um,
Wait. Okay. Can you guys hear me or just Bow?
We can hear you, Danny.
Okay. Good. Okay. Thank you.
Yeah.
All right. I'll wrap this up so there's time for questions. Sorry about that. My headset died. Um, okay. And you can still see the slides and stuff.
Yes.
Yes, we can see.
Okay. Wonderful. Okay. So we put those designer receptors into the parafacial zone. We can activate them with our designer drug and enhance slow wave sleep. And this is the most targeted method for enhancing sleep. These are the three different designer drugs that we're rotating through. They've been developed to specifically activate those receptors that we're expressing in the parafacial zone. And then for how we induce epilepsy in the mice, unfortunately, we have to do that. So we do it in as targeted of a manner as we can. We insert a cannula into the brain to hit the basolateral amygdala, and then we inject canic acid, which is an excitotoxin. And so this causes the neurons there to fire like crazy. The mouse seizes a bunch and it causes damage in the hippocampus. So this is a normal, healthy hippocampus. The mouse was just injected with saline, salt water. And when we inject canic acid, you can see that there's been damage done to the hippocampus. These cells are missing here and here. And this is similar to humans with temporal lobe epilepsy, the damage observed here. And they express, the mice have sleep deficits similar to people with epilepsy. And they also have spontaneous seizures similar to those people. So it's a pretty good model. To put all of this on a timeline, I make that injection to express the designer receptors. 2 weeks later, we put that head plate Bao showed you onto the mouse's head. Then the mice are tethered for a week. There's a mouse tethered up with the head plate, plugged in with this. We record a week of baseline. Then we induce epilepsy. We put that cannula into the brain to hit the amygdala and make that injection of the excitotoxin. We get a week of epileptic baseline. And then we have 2 3-week treatment periods where we're either giving that designer drug or just vehicle treatment, which is just the jelly, nothing else. So it's the vehicle that the drug is carried in. And here's a video of some of the mice eating those jellies that Bao talked about. It's a really awesome method because we don't have to give the mice daily injections. We can just drop the jelly into the cage, they'll eat it and self-administer the drug. So, uh, what does the sleep enhancement look like? So here I have a single mouse, epileptic mouse, that was having its sleep enhanced. And I have time and slow wave sleep here on the y-axis, and Zeitgeber time, which is just hours, but it's 0 to when the lights come on. And what I'm showing you is when the mouse gets designer drug or the mouse gets vehicle. And you can see that when the mouse gets the drug, it spends significantly more time in slow wave sleep than when it gets the vehicle. And not only does it spend more time in slow wave sleep, it also has a greater average slow wave sleep bout durations. When it goes into slow wave sleep, it's staying in that state for longer. So the sleep is more continuous, which you can see how increased that is compared to vehicle treatment. So for the first time, we have epileptic mice with this model of sleep enhancement, sleeping more and sleeping more continuously. So how is that affecting seizures? If patients with epilepsy have more seizures with worse sleep, hopefully we see a reduction in seizures with better sleep. So far I have the data in 2 mice that I'm going to show you. And here I have daily seizure frequency. So this first mouse was on, right, we have the crossover where the mouse gets 3 weeks of drug and 3 weeks of vehicle. So this first mouse was on drug treatment. It crossed over to vehicle treatment and had relatively more seizures during vehicle treatment. And this second mouse was on vehicle treatment first, crossed over to drug and had significantly less seizures during drug treatment. So it seems like seizures are going down with the improved sleep. What's really cool is if I show you each seizure and when it occurred. So here I have Zeitgeber time on the y-axis again. So that's just the 24 hours of the day. And then every dot here is a seizure. So, and then here the red line is when we gave the dose of either the drug or the vehicle. When I give the drug to the mouse, you can see that there's this period of roughly 10 hours where no seizures occurred for that mouse. And then they only occurred later in the day. The mouse crosses over to vehicle and it's having seizures whenever. This is even clearer for the other mouse, and it's a really exciting piece of data where this mouse was having seizures pretty indiscriminately throughout the day, right? Didn't really matter hour of the day. If the mouse was getting just a vehicle, normal sugar and water jelly, it was having seizures whenever. Crossed over to drug, started getting that designer drug to enhance slow wave sleep, and this period of seizure freedom opens up. And the sleep is only being enhanced for 2 to 3 hours, and yet the seizure freedom is lasting for 8 to 10. So it might be doing something to bring the circuit back into balance. There's some evidence that when people with epilepsy are sleep deprived, right, they have more seizures and their cortical excitability is higher. So maybe helping them sleep is bringing that circuit back into balance. So in summary, slow wave sleep enhancement, epileptic mice can be achieved. Oh, I didn't actually show you that figure, but that's also just raw data evidence that it can be achieved. It reduces daily seizure frequency and it shifts seizures away from the effect period, the effect being the enhanced sleep. And this work is proof of concept for slow wave sleep enhancement to heighten seizure control. And it's critical for, like I've described, that large untreated epileptic population. And it's relevant because there's a lot of ongoing research trying to develop ways to enhance slow wave sleep in humans. Uh, and so maybe this is like my nice acknowledgement slide for how science is always a team effort. Um, yeah, and Bao's on there. He's done great stuff contributing to the project. So I'd be happy to take any questions, or feel free to email me with questions about any of this or just grad school in general.
Right, well, if there are no questions for Danny right now, we will be sticking around later today in this meeting. And, there's context for Danny. We will send that additionally in the newsletter. But thank you again to everyone for staying through the whole entire presentation. Lauren will now be sending the attendance form. And yeah, thank you so much to Danny too with the amazing presentation, explaining your work and also your academic journey. It's been extremely insightful. And thank you to all those participants to standing by with all the tech issues. I do apologize for that, but I hope today's presentation has been extremely helpful in your introduction to neuroscience, sleep, and epilepsy. Yeah, other than that, thank you everyone. Lauren, if you could send the attendance form soon. Give us one moment. It's currently being processed.
Yeah, sorry, 1 second, guys.
Yeah, I'd also like to thank everybody for bearing with me through the the technical issues. Yeah.
Well, so let me see here. I will be sending the attendance form right now. Give me 1 second. Please let us know if there's any problems with that. Okay. If you finish the attendance form, feel free to leave at any time, but we're going to be around if you have any questions.
That was so many thank yous. My goodness. What's the attendance form for, Bao? You guys just
It's
keep
to
track of
collect
it?
data. To collect data. Also, it's a place where they can send in their questions too, and we'll give you access
Nice.
to that.
Cool.
Yeah. I like your background, Danny.
Oh, thanks. Yeah, I even yeah, I don't know. I think I could have been better about pausing for potential questions, but
Ooh,
yeah,
you have a question in the chat right now. Ziamara.
I do. Hamsters. I see. Um, that is interesting. Okay, so I have not. Oh no, you're fine. I have not. I've heard of some stuff with hamsters, but not a lot actually. Um, Mice are really popular because there's some really cool genetic tools that are only available in certain strains of mice. So the injections we make to the parafacial zone to express those designer receptors, um, I was saying like the GABAergic parafacial zones, we only want those receptors in those GABAergic neurons. We don't want them in all neurons. And so we have like a special strain of mice that's going to make us the receptors only get into those GABAergic neurons that we want. So that's why we work with mice because they have that special genetic tool. But I think I've heard of some stuff with hamsters. Yeah, especially I think people used to use more rats even because they're a little bit bigger. But ever since you can look it up like Cre recombinase. Um Cre recombinase. That's like the really awesome genetic tool that's with mice where you can basically turn off and on a gene or only target certain neurons that express certain proteins. It's really, really powerful. So that's why mouse research has gone way up. Yeah, cool. All right, now is it just gonna be like you guys just do some kind of uh admin stuff? Am I good to head out?
Yeah, you're good, Danny. Thank you so
Okay,
much.
cool. See you guys. This is very, very cool.
Thank you so much for your time. We
Of course.
really appreciate it, your
Lauren,
Thank
are
you.
you?
patience.
Oh, thank you. Lauren, are you the Lauren working with Kat?
Yes.
Cool. Okay.
Cool, yes. Nice to see you
And
again.
Kat talked, right?
Yeah, on Friday.
So she must have killed it, right? She's
You
great.
guys both killed it.
Oh, thanks. Okay. All right, see you guys.
Thank
Bye,
you.
Danny. Thank you.